if you chose to take discrete and stats next year, or 098 and stats or something with stats, this will kind of prep you for that. And if you took CAT or consumer, then at least you're getting like kind of a brief overview of what stats is like, okay, before you leave. So it says that a discrete graph is a graph of isolated points, and a continuous graph is a graph of points that are connected by a line or a smooth curve. Okay, and so data can also be described as discrete or continuous. Discrete data is when data has possible values that are countable and often finite, like it stops at some point. Data that's continuous can take on any numerical value within this range. Okay, so an example of a discrete type data would be like the number of people in a room. Okay, it's countable, like 1, 2, 3, but you're not counting everything between 1 and 2. Okay, because you can't have parts of people, hopefully, right? Okay, number of cookies in a box. I guess we should probably say like whole cookies in a box in case they're broken. Okay, and your graph for discrete is going to be like just points, okay, separate points. They're not connected. Continuous data would be like the temperature when heating up an oven. So it might say on the screen of your oven like it's 270, 271, 272, but it has to continuously heat up. So it's going to heat up in between those ranges, okay, at some point. How about like the amount of water in a tub as it fills? Okay, that it doesn't just jump from like, oh, you have like 1 foot of water to, oh, now you have 2 feet. It's that whole part in between the 1 and the 2. Okay, and so that's called continuous. So it would be like more like a line. It doesn't jump from one to the next. No, it could be a straight line too. Okay, it's just that it's connected. It's all those points in between. Good question. Anything else? Okay, suppose that you wanted to analyze battery life of comparable models of phones that 2 different cell phone companies offer. One way to display this continuous data is by using a relative frequency table. A relative frequency is the ratio of occurrences within an interval to the over the total number of occurrences. Okay, so you're going to do the number in that particular interval over the total, and that's going to give you the relative frequency. Okay, so let's try it on the back. Calculate the relative frequencies for various battery life intervals of phones from each company in the given tables. Okay, and this is just a couple of vocab terms. A population represents all possible data of interest in the study. Okay, all possible data. This study has displayed data for a sample, which is a subset of that entire population. So when you talk about, like, if we wanted to do an experiment on all the students at LTHS, all the students would be the population, and then maybe I'm just going to sample you guys. You would be the sample, okay? Each interval includes the first value but does not include the second value. So, for example, 8 to 8.5 includes the phones with battery lives greater than or equal to 8 and less than 8.5. Okay, so it's not including that second. That's not real important here, but okay. To find the relative frequency, we're going to take the number of phones in each interval and divide by the total. So the first thing you have to do is find the total number of phones. So add up all these numbers. It's 100. Okay, so now you're going to take 1 divided by 100, and that's the relative frequency for this spot. So 1 divided by 100. would be 0.01. Okay, then you're going to do 2 divided by 100, so that's 0.02, 0.17, 0.30, 0.32, 0.15, 0.03, and then 0. These are your relative frequencies. Any questions on where those numbers are coming from? Okay, why don't you guys do it here for the unlimited? I believe there's also 100 phones. Okay, so you should get 0, 0.01, 0.14, 0.37, 0.36, 0.11, 0.01. You okay there? Okay, so for continuous data, relative frequency histogram displays continuous intervals on the horizontal axis and relative frequency on the vertical axis. Right. So it says create a relative frequency histogram to represent the battery lives of the 100 cell phones in the samples. Okay, so from 8 to 8.5 for the E phone, we're only at 0.01, so we're up like very tiny little bit. Okay, then 8.5 to 9, we're at 0.02, so it goes up a little bit more from there. The next interval, we're at 0.17, so we're a little bit higher than 0.15. Next interval, we're at 0.30. We're going to go up again. And then 0.32, so it's up a little bit higher than that. And then 0.15, so we're back down here. And 0.03. And then 0. 0, you don't draw anything. Okay. Okay, so it should look something like this. Here's your bar graph. So it says, describe the shape and spread of the histograms. What might be the characteristics reveal for, or what might the characteristics reveal for each company? Okay, so what did we think? And you don't really know any terms, so just describe what you see, kind of. Okay, so it's increasing and decreasing in general. You know, I mean, this one keeps, then goes back up, but in general, yes. Okay. So can we say like it peaks in the middle? Good. Okay there. Okay, so if we were to say that the 10 was the mean or the average phone life, then we would have to say, or phone battery life, then we would say unlimited has more phones near the mean battery life, because this is higher peaked in the middle here, the 10. More of their phones fall near that mean battery life than that company. Okay, flip it over. Relative frequency histograms shown represent the sample of 10,000 phones. Okay, so from 100, now we're at 10,000 phones from each of the two companies. Compare these histograms created out of 10,000 sample phones compared to the only 100 cell phones. So what do you notice when we raise the amount of phones we're sampling? Doesn't change a whole lot, but I would say that I guess a little bit more data is kind of clustered towards the mean, and so these ones are lower, and then these ones are maybe the same, Okay, but we have a bigger percent of phones that are near the mean. Okay, so the higher, and this should happen, the higher the sample size, closer the data is towards the mean. Okay, so more data is clustered kind of around the mean. So the more sample that you take, the closer you should get to that average. Okay. These histograms below show the same sample of 10,000 phones, but now the data has been divided into intervals of 0.1 hours instead of 0.5 hours or half an hour. Okay, compare these histograms with the histograms from the previous question. Okay, and so in these ones, we're getting more specific data. Okay, it's kind of broken down. It's not as much of a curve. It's very choppy, and it's more broken down for closer data. Okay, so on the back it says, as the sample size continues to increase and the interval size continues to decrease, the shape of each relative histogram will likely start to resemble what we call the normal curve. A normal curve is a bell-shaped curve that is symmetric about the mean, meaning there's the same amount of data below the mean and above the mean. Okay, that's what they mean by symmetric. A normal curve models the theoretical data set that is said to have normal distribution. Okay, the normal curves for ePhone and unlimited cell phone battery lives are shown. In order to display a normal curve for each data set, different intervals were used on the horizontal axis in each graph. Okay, it says the vertical axis of the graph and the normal curve represents relative frequency, but normal curves are often displayed without vertical axis. Okay, so anytime you see this sort of bell-shaped curve, that's what we call the normal curve. And so we're going to say that these values are our mean. Okay, and then we'll talk about standard deviation on Monday, but this represents how far away from the mean it is, represents our standard deviation. Okay, it says, although the normal curves can be narrow or wide, all normal curves are symmetric about the mean of the data. Okay, so if you look at these first three graphs, those are all called normal curves, even though one is higher than the other. And each one has a mean right in the middle here. We use X with a bar over it to represent the mean. Okay, these ones would not be normal curves. Okay, and we'll talk about what these are called on Monday. Okay, but these ones would not be normal. So if you just had to pick out a normal curve, they have to be symmetric about the mean. Okay, that's all we're going to do today because I wanted you to have no homework. So you guys can just work on your homework the rest of the time. Okay, so Monday, we'll talk a little bit more about vocab, and we'll kind of get into more specifically what we're going to do in this chapter. Okay, so let me get your homework. Okay, so the first 6 questions just say, is it continuous or discrete? Okay, and then 7 asks you to do a relative frequency table and then a relative frequency histogram. 8 says the same thing, okay, and then at the end it says, does it approximate a normal distribution? While you're working on this or after you're done with this, if you had questions on your throwback chapter 11 worksheet you worked on yesterday, I know Miss Sable